Learn Physics at Home, episode 1.2, part 1, resolving vectors. Now, this is a very important lesson because this is going to affect all sorts of things later on in mechanics. So this is going to affect things like projectile problems and force diagrams and a whole host of other things where we see resolving vectors being important. So in the last episode, we said that a vector was a quantity that had magnitude and direction. So let's take the most simple vector that we could possibly have, which would just be an arrow to the right. So that arrow actually has two things that it tells us. It tells us the magnitude, which is going to be the length of the vector, and the arrowhead tells us the direction. So there's two pieces of information encoded within that. The length is the magnitude and the arrow tells us the direction. So let's say that that vector represents a force, and we could just say that it's 10 newtons. A vector that's half as long would then be only 5 newtons. And obviously a vector that's twice as long would be 20 newtons. But vectors can be represented for any quantity. This would be force because it's in newtons, but we could say that that's a velocity vector, which would be 5 meters per second. Or it could be acceleration, which is also a vector. We could say 2 meters per second squared. And again, if this was half as much, that would be 1 meter per second squared. But let's look at this direction specifically. It's to the right. So we can define that a couple different ways. We could say we have coordinate directions of north, south, west, and east, and that vector is to the east. We could also set up a coordinate system where we say to the right is positive, to the left is negative, so that would be positive 10 newtons. So our direction would be, again, encoded within that number. F equals 10 newtons. It's positive, so it's to the right. So we can say the same thing is true for vectors that are up. So if we have a vector that's straight up, we could say that that vector is 20 newtons. So a vector that's half as long would be 10, or twice as long would be 40. But that could also represent a velocity of, let's say, 3 meters per second, or an acceleration of 12 meters per second squared. Whatever that happens to be, that's what that vector represents. So this is all basic. It's very straightforward. But what happens when we have a situation where the vector is at an angle to our coordinate system? So this first situation that we can look at would be doing something like having a vector that is at an angle to the horizontal axis. So let's say I have a vector that's coming off of here. We'll do this approximate. I'm not going to actually measure the angle. But let's say that this angle is 30 degrees and that the length of this vector gives us a value of 10 newtons. We're in newtons, so we know that's a force. This vector contains both up components and to the right components. In other words, this vector is up and to the right, but part of that vector is up and part of that vector is to the right. We can figure out how much of that vector is to the right and how much that vector is up, and those are called the components. I'm not going to do this perfectly, I'm just going to freehand it, but if we have a line that comes down here like this, and that forms a right angle, then our horizontal component goes out here and extends to where those cross, and that's where the tip of our arrow goes. So this right here is our horizontal component. So if I call this F, that's our resultant force, then this would be F of x. If we do the same thing here, and I put in a nice right angle here, and I follow this across from here, making a rectangle, I have another right angle in here, and this upward component is going to travel, and we're going to draw the arrowhead right where those cross, like that. So that's going to be the upward component of this coming over. So that's going to be our F of y. But how do we find F of x and F of y? Well, if we have a right triangle, we can use right triangle trigonometry. In this case, we want to know the horizontal component, F of x, and we have the resultant force, 10 newtons, and an angle. In this right triangle, we have the adjacent and the hypotenuse. Now, if you remember from math, we have SOHCAHTOA. So our SOHCAHTOA tells us with adjacent and hypotenuse, we want to use CA. So we're going to say cosine theta equals adjacent over hypotenuse. So put our numbers in. We have cos 30 equals adjacent, that's our F of x, and solve or put in 10 newtons for the hypotenuse. Cosine of 30 is 0.866, and multiplying 8.66 times 10 is going to be 8.66. So we have F of x equals 8.66 newtons. What is this? This is the amount of 10 that's going to the right. In other words, if we were pulling, let's say, a sled, 10 newtons of force would be acting on the sled, but only 8.66 newtons would be pulling to the right. How much force would be acting up on the sled? Well, now we're solving for F of y. And because we have a rectangle, this side of this triangle is also equal to this side of this triangle. Well, now we have an opposite and a hypotenuse, so we can use so. So we say sine theta equals opposite over hypotenuse. Sine 30 equals opposite, that's our F of y, over hypotenuse, which is 10 newtons. Then we solve, cross multiply. Sine of 30 is 0.5. 0.5 times 10 is 5. So our F of y is 5 newtons. Again, this is crucial to understand. There is only one vector. That vector is 10 newtons, and that vector is at 30 degrees above the horizontal. But these components are the parts of the vector that represent how much of this vector is to the right and how much of this vector is up. Let's look at a real-life example working in reverse. So this time we're going to be given the components and we're going to be looking for the resultant. Let's say we have a boat, and the boat is crossing a river. The river is flowing downstream, we'll call that to the right, at 4 meters per second. So although the boat is going to travel straight across the river is also going to be moving the boat down the river. So we can see that if the boat pushes itself this way and the river pushes it this way, the boat's going to go off in some direction this way. So what exactly is that direction? And what's the magnitude of that? Well, we know that the magnitude has to be the resultant of those two vectors. So let's go ahead and re-sketch this out. So we'll say we have a vector of 3. keep our units on there, and 4. And of course, we're not doing this perfectly to scale. And then we're going to draw in some boundaries here, which are going to be the rectangle that's going to help us to see what the resultant is. So our resultant is going to be the line that goes up exactly to where those cross, and the tip of the arrow is going to hit that crossing point. So this is our resultant, and the length of that resultant is the magnitude. It's the resultant velocity of these two vectors. So we don't know what this angle is, but we can find it. So we have a right angle right here, and therefore we have a right triangle. And if this side of the rectangle is 3, this side of the rectangle is 3. So let's go ahead and find the angle first. We have opposite and adjacent, so that's going to go with tangent. Tan theta equals opposite over adjacent. So we're going to do tan theta equals opposite, 3 meters per second, over adjacent, 4 meters per second. And on your calculator for this one, depending on what kind of calculator you have, you're going to have to do the second tan function, which is tan to the minus 1. So on this, it's second tangent, and that's going to be 3 divided by 4. And that gives us 36.86. So we'll just round that to 36.9. So theta equals 36.9 degrees. To find the resultant, we can do Pythagorean theorem because we have two sides of the triangle. So we have a squared plus b squared equals c squared. And we have 3 meters per second squared plus 4 meters per second squared equals c squared, which I'm going to write as r for resultant. When you do this, you might already be able to see I picked some easy numbers here. That's a 3, 4, 5 triple. So the resultant is going to be 5 meters per second. Now, because it's a vector, we can't simply say 5 meters per second. So we would say 5 meters per second at 36.9 degrees above the horizontal. The tip-to-tail method is a way of resolving your vectors in a diagram to make sure that your resultant vector is going the correct direction. So let's take an example of two vectors that are at right angles to each other. But in this case, they are tail to tail, the tail being the end of the arrowhead being the other end. So what we want to do to find the resultant vector is to move one of the vectors into a position where the tail is touching the tip of the other vector. Well, you can see if we take this vector and just slide it up here, we can do this. Now, this should make sense because we haven't changed the direction of this vector, it's still to the right, and we haven't changed the magnitude because the length is the same. So if we get rid of this vector, now we can do the tip-to-tail method. And the tip-to-tail method says that we go from here all the way up to here. And this is our resultant R. Let's just look at one that goes the other direction because we've been doing so many that are the same. Let's say we have a vector to the left and down. Then we can take this vector and slide it down and do the tip-to-tail method. Or we could move this vector and slide it over here. Let's do that just to do something different to show that it still works. Oh, the point of that vector is there. So we slide that vector over here, and the tip-to-tail gives us our resultant like that. That's our resultant. There's another method for doing vectors, and we can do the resultant vector by doing vectors to scale. In this case, I actually used a protractor with a little ruler in there to measure this out. So this is exactly 4 centimeters. And this right here is exactly 6 centimeters. So if we pick a scale of 1 centimeter to 3 newtons, then we would just multiply. So 3 times 4 gives us 12. So this vector would be equivalent to 12 newtons. And this vector right here, 6 times 3, would be equivalent to 18 newtons. Because it's to scale, our resultant vector, which is going to be using the tip-to-tail method, is also going to be to scale. So the length of this vector r is actually going to be exactly equal to what we measure it to be, which is 7.2. So this is 7.2 centimeters. We could have done a squared plus b squared equals c squared, and that would be 4 centimeters squared plus 6 centimeters squared equals r squared, and that actually ends up giving you a resultant of 7.2 meters. The other option that we can do here to figure out the resultant in newtons is multiply 7.2 times 3, which gives us 21.6 newtons. Equilibrium occurs when the total vector sum equals 0. Now, because vectors have direction, if we call to the right positive and we call to the left negative, then we're adding things that have negative values. For example, if I have a vector, and typically this is done usually in the force unit. So let's say we have 10 newtons to the right. To get this system in equilibrium, we would need to have 10 newtons to the left. So this is a negative 10 Newton vector and a positive 10 Newton vector, which gives us a vector sum of 0. We could also say we have a vector up of 3 newtons and down of 3 newtons, and this system would still be in equilibrium. What might be a question? Well, you could have something like this, where you're given 10 newtons and 3 newtons, and the question might be, what force do we need to apply to put the system in equilibrium? And the answer would be a 7 Newton vector to the left, or we could say negative 7 newtons. Now this can get a little bit more tricky when we have vectors at right angles. Let's go back to the one that we've been using before, which is 2 component vectors. And what would be the vector that we need to find equilibrium in this case? Well, that would be the vector that is opposite the resultant vector. So we resolve the vector, and then what would cancel out this vector? Remember, these are only the components. There's actually only one true vector. It's this. Let's give it a made-up value. Let's say it's 15 newtons. Well then, to cancel out 15 newtons, we would have to have a vector going in the opposite direction of 15 newtons. And there's actually a name for this. It's called the equilibrant. Finally, we have the parallelogram method. The parallelogram method is used for finding the resultant of 2 vectors that are not at right angles to each other. So in this case, we have 2 vectors. I'm actually going to extend this vector out and then use this point right here at the tails. And then I'm going to line this edge up with this vector, and you can see I'm off a little bit, but it's about 30 degrees. So to find the resultant, we can't draw a rectangle, we need to draw a parallelogram. And it'll sort of make sense once you see it. So what we're going to do is we're going to take this vector, and just like before, we're going to slide it over tip to tail over to here. But we have to make sure that that vector has the same angle as it does here. So we come up here, and we align our left side of the protractor, our dot in the middle, and then we're going to come over here and put a little mark at 30 degrees. So we know that the vector is going to be parallel to this line right here. So this line and this line are parallel. But I can't draw the vector yet because the vector has to have the same magnitude. It has to have the same length. So we look at the length of this vector, and it's 4 centimeters. So I'm going to come over here and draw that at 4 centimeters. And I'm only putting that dot in there so that I know how far, what's the magnitude of that vector. And that's going to be that right there. Now, what's my resultant? Tip to tail method. That's my resultant, R. To find the value of this, we can use the scale the same way that we did before. But if you want to do the mathematical value of this, there's 2 different methods that I'm going to leave to my AP Calculus course.